Hello everyone. I would like to show now the results of these two theorems combined, theorem 4.1.4 and 4.1.5. So it basically tells us that if you have a higher order linear ODE, then those two theorems guarantee that there is a fundamental set of solutions. So there are n functions that combined form the general solution. So just to illustrate that theorem, let me show you an example. This is actually example 9 on page 125, if you want to take a look at that. So here is the OD. It has a third derivative there, minus 6y second derivative plus 11y derivative minus 6y equals to 0. So notice that this is a linear ODE, and we learn how to solve first order ODEs, right? Like if we have only this part here, we know how to solve. We can solve by linear method or by separation of variables or even exact equations. But in this chapter 4, we're talking about now high order ODEs. Now what this theorem is saying is that this ODE here, it's linear because the coefficients are certainly functions of x. Well, in this case, it's even more simple here because the coefficients are simple constants. So it's linear. So the theorem guarantees that because it's third derivative, that's the higher order, the highest order, or the highest derivative. So it's the third order differential equation. The theorem guarantees that there are three solutions. So what the theorem is saying is that there are three independent or linearly independent solutions. So let's call y1, let's call them y1, y2, and y3, okay? Linearly independent means that you cannot obtain one from the other. So they're kind of the building blocks of all other solutions that are out there. So it means also that these are the minimum number necessary to construct all the other solutions. So if you had only the first two, then yes, this is linearly independent, but there will be some solutions out there that you wouldn't be able to construct from these two. So you need the three solutions in order to construct all the other solutions. So that's why it's called fundamental set. It's the building blocks of all other solutions. So there are three linearly independent solutions, and in this exercise, they give you these three solutions. Okay, we're going to learn in the next few sections how to find these three solutions or how to find these fundamental solutions. But in this exercise or in this example, they give you the solutions. They say, okay, y1 would be e to the x, y2 is e to the 2x, and y3 is e to 3x. Yeah, it looks like there's a pattern there. We'll see how that pattern comes about when we try to find these later. Anyway, these are the three linearly independent solutions. Because they're linearly independent, it forms a fundamental set. So those are the minimum number of solutions that can construct all the other solutions that could exist. Now, they give you these three solutions, and then they say, okay, they first ask you to check. Well, they don't ask you to do that, but it's a good exercise to check that each one of these three satisfies the ODE. And it's very simple to check. Like, for example, let's check this one here. And the third derivative of e to the x is e to the x. So let me check. Okay, let me write this here. Check if y1 equals to the e to the x is a solution. So if I plug e to the x into the ODE, third derivative of e to the x is e to the x minus 6 times second derivative of e to the x is e to the x plus 11 times first derivative of e to the x is e to the x minus 6 e to the x. Is that equal to 0? And you will see that it is, right? So this is 1 with the 11, that's 12ex, and then negative 12ex, it is 0. So it is a solution. And you can check the other ones, and you will see that they are also solutions, like y2 equals to e2x, let's check. Okay, the third derivative of e to the x, okay, the first derivative is 2e to 2x. The second derivative is 2 times 2e to 2x. You can try that, okay, here. So e2 is e to 2x. e2 derivative is 2e to x. Second derivative is 4e to x. And the third derivative is 8e to x. And if you put those in here, like 8e to x minus 6 times the second derivative, that's times 4e to 2x, plus 11, and then first derivative here, that's 2e to 2x, minus 6 times the function, which is e to 2x. Is that equals to 0? Well, see, this is 8 minus 24, that's negative 16. Negative 16 plus 22, that's 6, right? Positive 6. And then minus 6, that's 0. Yes. So it works. Okay. And you can check the third one as well. So you will see that it is a solution. Okay, so there are solutions. Now, the second question is why they are linearly independent. Well, if you compute the Wronskian, so let's calculate the Wronskian of these three functions, e to the x, e to the 2x, and e3x. So put that in here, the three functions, ex, e2x, e3x. And then put the first derivatives here, e to the x, 2 e2x, and 3 e3x. And then the second derivative, ex, will be 4 2ex. It's the second derivative of that. And the second derivative of this would be 9e3x. Okay? So that's the determinant. Now you can compute the determinant by hand. I'll let you research that. Okay? It's not that hard or bad. It's just time consuming. So you can do that method of multiplying lines like this. Okay, so I'll let you research that. Anyway, if you compute the determinant, it turns out this would be 2, I'll just copy here from the book, 2 times e to 6 to the x. Now, is this, can this function be equal to 0? Well, it doesn't matter what x is, this will never be 0, because it's e to 6x. X can be 0, so this would be 1, can be negative numbers, so this is never 0. Okay? So this is different than 0 on the whole real line. So if it's not 0 on the whole real line, that means that ex, e2x, and e3x are linearly independent on any interval, or in particular, or in general. We pick the biggest interval, that's the whole real line. So good. So because now we found 3 linearly independent, well, we didn't find, they gave it to us. Because we found 3 linearly independent solutions, and the theorem says that if we have n of them, or 3 of them, right, it's the third order. If we have 3 of them, that means they form an fundamental set of solutions. So e2x, e3x is so this set here is a fundamental set of solutions. So those 3 guys are the building blocks of all the other solutions. So any other solution of the same ODE, any solution of this ODE here has to be written in terms of these 3 guys. Okay, it's a linear combination of those 3. So that's why we say the conclusion of the theorem says, so any solution, the general solution, is a linear combination of those 3 solutions here. So we can say the general solution, any solution, is a linear combination of those three functions. So what the theorem is also saying, well, because of that, is that if there is another solution out there, okay, if someone says, hey, I have a solution here of the ODE, then you can say for sure, okay, that solution that you have in your hand has to be, has to look like that. It might be like, I don't know, just 3 times the first one, or maybe 4 times the first one minus 2 times the last one. It has to be written in this format here. Okay, there's no other way. That's what it's neat about the theorem. Okay. All right. Now let's go to section 4.2 and talk about now a little tool that we're going to use to find these solutions. Okay, so remember that now the question is, how do we find these guys in the first place? Okay, how do we find e to the x? And how do we find the other ones? So that's what section 4.2, 4.3, and the remaining of the chapter is about, finding those guys. So I'm going to show you a little tool called reduction of order. And the idea of reduction of order is this. So let me write section 4.2. Reduction of order. So the idea here is to, from one solution, so if I have just one solution of the ODE, then I should be able to find another one from that first solution. From one solution, we will find another one. So this will be for, this is for second order ODE. Okay. Linear ODE. So let me show you how do we do this. So it starts on page 131. So let's look at one example. Okay, here's the ODE. Let's start with this one. This is a second order ODE, linear ODE, because it has a second derivative. And let's say we know that one solution is e to the x, okay? If I put e to the x here, second derivative is e to the x minus the function, which is e to the x, that's 0. So it is a solution. Now, how do I get another one from this one? Well, you know that if I multiply by a constant, yeah, that's another solution. Yeah, we saw that if we go back to section 4.1, if you look at the superposition principle on page 121, if you have a solution, you multiply the solution by a constant, or if you have two solutions and you add them up, you get another one. But when you do the superposition principle, the new solution that you get is dependent on the first one, on the ones that you've started with. So this one here is from e to the x. Yeah, I got a new solution here, right? Let's say, for example, I multiply by, I don't know, 4. Yeah, this is another solution. This is a solution. This is another solution. By simply multiplying this solution by 4, I found another one. But the problem is that this one here is, this one and this one are dependent, right? Because I can write this one as a linear combination of the first one, which is simply this new one that I got here is the solution times 4. So it's dependent. It's linearly dependent. But the goal here is to find, so I forgot to say here, find another one that is independent. Well, let me rephrase this correctly. It's that is linearly independent. Independent from the first one. Okay. So this one here doesn't help much because it's dependent. So the goal is to find a y2 that is linearly independent from y1. Okay, so that's the goal here. So let me just write here two solutions, two different solutions, but they are linearly dependent. Okay, for this one here. So that's why this doesn't help much. Okay, so how do we find that? Here's the trick, how to find the second one that is linearly independent from the first one. You simply, that's the trick here, you're gonna write u2 being, y2 being a function of u times the first one. Okay, so that's what that's the idea in that example. So in this case, in this particular example, we want y2 to be, okay, y1 is e to the x, so this would be e to the x times ux. Okay, you may ask, okay, how do you know that the second one will be u, whatever that u is, times the first one? You know, that's it shows, the exercise shows that those two, if you do this, it will be linearly independent from the first one. Okay, so that's the technique. That's they call it reduction of order. All right, let's see how we find this function here. Okay, it's e to the x, so the first one times some function u. Okay, how we find that? So here's the idea. So we need to plug that into the original ODE. So we have y second derivative minus y equals to 0. Okay, if this is a solution, then it needs to satisfy the ODE. So okay, what is the second derivative of that function to y2? Well, that's ex, derivative of the first times the second, plus the first times the derivative of the second. Well, let me find the first derivative, which is easier. Okay, so find the first derivative there. So let me simplify the notation. I'll just say ex u plus ex u prime. Then I can factor ex. So this will be just simply u plus u prime. I don't know if I need to do this. It doesn't look like I need, because things are going to simplify. Anyway, well, let me just leave it like that. Okay, what is the second derivative then? All right, second derivative of this first one, that's ex u plus ex u derivative. Plus, now, second derivative of this second term, ex, derivative of the first times the second. I'm calculating the derivative of the second term. The derivative of the first times the second, plus the first times the derivative of the second. Okay, let's plug all of that in here. Okay, let's see, this would be, I can combine things in here. See this one here? It's twice. Okay, it would be ex u plus 2ex u derivative plus ex u second derivative. And then minus the function, which is just a solution, ex u. Okay, and okay, so this will cancel with that. Then I can factor ex, then this would be 2u derivative plus u second derivative, and that's equal to 0. All right. Okay, and in order for this to be 0, well, this guy here needs to be 0, right? Because the exponential will never be 0. So that means, so let's write this way here. So this implies that 2u derivative plus the second derivative must be 0. Okay. All right, and then this is easy to solve. We can consider this guy here to be some other variable. Let's call w. The book calls it w. So if this is w, this is w prime, right? So we're just reducing. That's why it's called reduction of order. Now we have a variable u, where we see the first derivative and the second derivative. We can substitute that with another variable, so call that w. So the second derivative will be w prime. Okay, why couldn't we do this in the first one? Well, the problem is the first one here See, we have the second derivative, but we have the function, so it's hard to do the substitution. Here we don't see the function. We don't see u there. We just see the derivative and the second derivative. So that's why we can reduce. If we had a u here, then we couldn't call that w because we wouldn't reduce the order, right? So we're reducing the order because we don't see the variable u there. So I can view that as 2w plus w prime equals to 0. And this we know how to solve. We know how to solve this. You can use separation of variables, linear, any of the other previous methods that we used before. So because it's linear and it's the first order. Okay, so let me give you the solution for w. So w here would be, it would be constant c1 e negative 2x. Okay, so you can check that, you can solve that and see it will look like that. Well, okay, now let's substitute u back here. This means that u, because w was u derivative, so this is c1 e negative 2x. Well, now a little integration here to find what u is. Integrate that, and this would be integrating that will be negative 1 to c1 plus another constant c2. Okay. So therefore, the second solution, which is, remember, it was ex times u, function u. So this would be ex times that. Plus c2. So this would be negative 1/2 c1, and then negative x plus c2 e to the x. Okay. All right. We can pick. Let's pick constant. There's no initial value here. So let's pick, for this particular case, there's no initial value. We can pick, for example, c1 to be, just copy the numbers here, c1 equals to negative 2, c2 to be 0, just to make it a nice e to negative x. So I can consider y2 to be e negative x. Okay? So we found, well, we had y1 to be e to the x, and we found another solution, e to the negative x. Good, we found another solution. Now the question is this second one here linearly dependent on the first one? Because if it's linearly dependent, then this whole work was useless because it doesn't help. We need to find two linearly independent solutions. Well, fortunately, if we do the Wronskian of that one with this one here, it turns out that if you do the determinant, so this will be e to the x, e negative x. Derivative is e to the x. The derivative here is negative e to negative x. So that would be ex times negative e negative x minus ex times e negative x. Right, so it's this one here minus that one. Let's see. Yeah. So this would be negative. Okay. Yeah. It's twice the same thing, right? So it's negative 2. Yeah. Negative 2. Well, e to the x times e to the negative x. That's e to the 0 power, right? Which is negative 2. So this is never 0. So solution 1, and the new solution we found are linearly independent. So we can say that the general solution of the original ODE which was what? Yeah, y double prime minus y equals 0 is a linear combination of those two guys. Okay. All right, that was just to show that we can obtain, in the case of a second order linear ODE, we can obtain a second solution that is linearly independent from the first one through reduction of order, so through this process here. And then on that same page, on page 131, the book shows a general case. Okay, what if we have any second order linear ODE? So the general case, so we can say in general, for y double prime plus px y prime plus q of y, oh, not q of y, q of x, y equals to 0. So in general, we can do the same thing, same idea, same process, but it becomes very complicated. Lots of algebraic manipulations. But the book gives a formula, and for now, we're gonna memorize this formula. So here is something that you need to remember, and I'll provide this to you. Just remember that we can obtain, so given a solution y1, we can obtain a second solution. So let me copy this here for you, which is the first solution times, and here it comes, integral of e integral of negative integral of px dx divided by the first solution squared. Okay, so don't worry, I'll provide this formula for you. It's just a matter of understanding what is this for, okay? Okay, what is this formula for? It's to find the second solution from the first one. And it turns out that this second solution here is linearly independent from the first one. So therefore, we are able to find two solutions. From one, we can find another one, and those two are linearly independent. Okay, so that's and then you can read example 2. It's just a matter of plugging numbers here, like whatever this is, plug that in here, compute the integrals, and you will find your second solution. Right?